Hey, so in this video, we are going to be talking about geometry. So we're going to be taking a look at the three-dimensional shapes of these molecules. This is going to come from the Lewis dot structure, so it's really important that you have a good handle on how to draw Lewis dot structures before moving on to geometry. So when considering and talking about the shape of the molecule or the geometry of the molecule, it's important that we focus on the central atom. So that is really where we're going to focus our attention here, is on that central atom. And so that central atom is the atom that's in the middle, and it's surrounded by the other atoms that are bonded to it. So we're going to be taking a look at two different types of geometries that are related to each other. And the first one is the electron geometry. This is defined as the shape determined by the total number of electron regions, and this is both bonded and lone pairs. Now, before I talk about why we care about the electron geometry, it's important to define exactly what we mean by that electron region. So the following all count as one electron region. A single bond counts as one electron region. Multiple bonds, so this would be double and triple bonds, count as one region. And each lone pair counts as one region. Now, the reason we care about this is that these electrons are going to try to get as far away from each other as possible. Like charges repel, and so that's going to push those electrons away from each other, right? They're all negatively charged, and so they're going to try to space themselves out to increase the distance. This is going to determine our molecular geometry, and that is the shape of the molecule, and that's what I just talked about, right? It is determined by the VSEPR theory, that is valence shell electron pair repulsion, which basically means that those electrons try to get as far away from each other as possible. We will do an example like this, and I'll show you how to go about doing that. If you have a molecule that has multiple central atoms, then it's going to be really important that each central atom gets its own geometry, electron geometry as well as molecular geometry. Okay, so what we're going to be doing here is we are going to be taking a look at the electron geometry and the molecular geometry and talk about how those are interrelated. We're going to focus on this particular chart, and we're going to step through exactly how to go about using this chart. Now, this chart is in your guided practice, and you are also going to be using this in lab, where you will actually get to make these compounds with models, either with using ball and stick models like this, or by using something called MolView. All right, so I think the best way to go through this is to go through some examples. And so I'll be stepping you through an example of each type of electron geometry and molecular geometry combination. As I am writing out, now these are all going to be based off of Lewis structures. So as we're going through and I'm writing out these Lewis structures, if anything feels sticky to you as far as the Lewis structures go, you're definitely going to want to go back and take a look at the Lewis structures podcast, or make sure you talk to your instructor to get some extra help. Okay, so the first compound we are going to be taking a look at is carbon dioxide. So let me go ahead and draw carbon dioxide up here. Make sure I give myself plenty of space. Okay, so in order for us to determine the electron geometry and then the molecular geometry, we have to take a look at the electron regions, and this is all going to come from the Lewis structure. So the very first thing I want to do is I want to identify my central atom. So my central atom, excuse me, is going to be the atom that's in the middle, right? It's going to be surrounded by my external atoms. So in this case, carbon is my central atom, so I'm just going to go ahead and draw a box around my carbon. And then what I want to do is I want to investigate and find the number of electron regions around that central atom. Remember that single bonds, double bonds, triple bonds, and lone pairs all count as one region. And again, I'm looking at the regions around that central atom. So for carbon, I have a double bond on each side of the carbon. Remember that double bonds each count as one region. So since I have two double bonds, I have two regions around that carbon. So for carbon dioxide, I have two electron regions. Now, I want to investigate how many lone pairs and how many atoms do I have around that carbon. Well, in this case, I have two atoms and I have 0 lone pairs. That means that the electron geometry and the molecular geometry are both going to be linear. That electron geometry is determined by where those electron regions are. Those electrons are trying to get away from each other. Right? You have negative charges, multiple negative charges. They do not want to be near each other. They're going to repel. And so the farthest they can get away from each other is 180 degrees. So this is what my carbon dioxide looks like. Here I have carbon in the middle and I have oxygen on either side. So it is a linear molecule. Okay. The next molecule we're going to take a look at is this guy right here. So I've got carbon double bonded to an oxygen. And then I have two hydrogens off of that carbon. Make sure I put my lone pairs on the oxygen. All right, so again, I want to focus my attention on the central atom. And so again, carbon is going to be my central atom. Right, carbon's right in the middle. And then I want to count up the number of electron regions around the carbon. I have a single bond, a double bond, and a single bond. So single bond, double bond, single bond is going to give me 3 regions around that carbon. And so now I'm going to investigate to see how many atoms and how many lone pairs do I have around the carbon. I have 3 atoms around the carbon, right? I've got hydrogen, hydrogen, and oxygen. So I have 3 atoms around the carbon, and I have 0 lone pairs on the carbon. That is going to make both my electron geometry and my molecular geometry trigonal planar. And you can see the drawing right here for what this looks like. And I have a model for you. So this is what this molecule looks like. I've got carbon right here in the middle. I've got my 2 hydrogens and my oxygen. So this is literally going to be like a flat triangle. So if I take it to the side, right, you can see that the oxygen, carbon, and the hydrogens are all in the same plane. It is flat. All right, let's take a look at my next example. So for my next example, I have oxygen. Oh, let's do a different color here. I have oxygen double bonded to a sulfur, single bonded to an oxygen. Let's get my lone pairs in here. All right, so around my central atom, sulfur is my central atom. And again, I want to count up the number of electron regions. So I have a double bond, I have a lone pair, and I have a single bond. So double bond, lone pair, single bond, going to give me 3 regions around that central atom. Now where it's going to be different is I have 2 atoms, right? I've got 2 oxygens connected to that sulfur, and I have a lone pair. So I have 2 atoms, those 2 oxygens, and I have a lone pair. The electron geometry is always going to be based on how many electron regions I have. So since I have 3 electron regions, the electron geometry will be trigonal planar. And if you notice, right here, rather than having an atom, I have a lone pair. All right, so that lone pair is going to influence that electron geometry and make it trigonal planar. But it is the number of atoms and lone pairs on that central atom that are going to determine the overall shape of the molecule. And since I have 2 atoms and 1 lone pair, that is going to make this molecule bent. And this is what this molecule looks like. I have sulfur here in the middle, and then I've got my 2 oxygens on either side. Again, I'm still in the plane, right? All of these atoms are still in the same plane. My lone pair is right up here, and it's causing these oxygen atoms to move kind of in a downward direction. And so that's where that bent shape is coming from, right? That lone pair that exists on the sulfur takes up space and it pushes down on these 2 bonds. Okay. The next molecule we are going to take a look at is CH4. Okay. So CH4, I have carbon here in the middle, and I have 4 hydrogens. That's terrible. I have 4 hydrogens around that carbon. All right. So again, I want to put a box around my carbon, around my central atom. And now I'm going to go ahead and count up all of the regions around that central atom. And I have 4 single bonds. So that is going to give me 4 electron regions. Now if I count up all of the atoms around that central atom, I have 4 hydrogens around that central atom. So I have 4 lone pairs. I'm sorry, I have 4 atoms, 0 lone pairs. That is going to make my electron geometry tetrahedral, and that is also going to make my molecular geometry tetrahedral. I hope you're starting to see a pattern where the number of electron regions, if the number of electron regions matches the number of atoms, then the electron and molecular geometries are the same. It's when the electron regions don't match the number of atoms that you're going to have a different molecular and electron geometry. Okay, so this is what this molecule looks like right here. So I've got my carbon in the middle, right, and my 4 hydrogens. Let's put that over my face so that you can see it. I've got those 4 hydrogens coming off of the carbon. One thing I want to point out, and you are going to see this potentially in your notes, is sometimes when we have a molecule like this, it's really hard to draw this 3-dimensionally, right? We're working with a flat piece of paper. And so what you are going to see, and just be aware of this, that you may see this in your textbook, is you may see that some of those bonds are represented with wedges and dashes. So where you see a straight line, so right here and right here, that indicates that those hydrogens and that carbon are all in the same plane. Whereas the wedge is showing that the hydrogen's coming out towards you, and the dash represents that that hydrogen is going away from you. So I don't know if you can see this here. Again, I'm going to hold this up over my face. So right here, these guys right here are all in the same plane, whereas one of the hydrogens is coming towards you, so it's getting blocked out, and the other hydrogen is moving away from you. Definitely really easier to see this if you actually build the models themselves. MolView is super helpful also in being able to see that. You can take that molecule and rotate it around. Okay, so I just wanted you to be aware when you see that, that's what that's representing. All right, let's take a look at our next example. I have NH3. So I have nitrogen and 3 hydrogens coming off of the nitrogen and a lone pair on my nitrogen. All right. So here, nitrogen is my central atom. And I have 3 bonds, 3 single bonds, and a lone pair. So that is going to give me 4 electron regions. Now, what I have here is I have 3 atoms that are surrounding that nitrogen, and I have 1 lone pair. So I have 3 atoms and I have 1 lone pair. Remember that the electron geometry is going to be determined by the number of electron regions. So 4 electron regions means my electron geometry is tetrahedral. 3 atoms, 1 lone pair tells me that the molecular geometry is going to be trigonal pyramidal. Now, here is what ammonia looks like. Right, I've got my nitrogen in the middle here, and it's surrounded by 3 hydrogens. And if you can see this, it looks like a pyramid where my nitrogen's at the top. And remember that I have a lone pair right up here on top of the nitrogen. Okay, so that's causing this to have this shape. Okay, the last one we're going to look at right here is water. And water is oxygen with 2 hydrogens and 2 lone pairs. So oxygen is my central atom. I have 2 bonds and 2 lone pairs, giving me an electron region of 4, which again means that my electron geometry is going to be tetrahedral. Now, I have 2 atoms and 2 lone pairs, right? So I have 2 atoms and I have 2 lone pairs. That is going to make the shape of this molecule bent. Okay, and so this is what water looks like, right? Water has, here's my oxygen in the middle, my 2 hydrogens on either side, and I have 2 lone pairs on this oxygen. So this does make this molecule bend. Okay, so the last thing I want to talk about is I want to talk about a molecule that has more than one central atom and how you go about figuring out the electron geometry and the molecular geometry for each one. So anytime you have a molecule that has more than one central atom, you are going to have to determine the shape around each central atom. All right, so let me draw the Lewis structure of our example, or for our example. So I have carbon that is bonded to 3 hydrogens. Okay, and that carbon is also bonded to an oxygen that is connected to a hydrogen. So here I have 2 central atoms. I have carbon, which is bonded to, has 4 bonds. And I also have, let's do orange for oxygen. And I also have oxygen. So what I'm going to want to do is I'm going to want to isolate each of these and talk about the shape for each of these atoms. So let's start with carbon first. So carbon has 1, 2, 3, 4. Carbon has 4 electron regions. It has 4 atoms and 0 lone pairs. And so for carbon, the electron geometry and the molecular geometry are both going to be, it'd be nice if I could write here, would both be tetrahedral. Now for the oxygen, and I'm going to highlight oxygen. Let's do green. For oxygen, I have 2 single bonds and I have 2 lone pairs. So for oxygen, I have 4 electron regions, which means that my electron geometry is tetrahedral, but I also have 2 atoms, 2 lone pairs. So my molecular geometry for my oxygen is bent. Again, my oxygen has an electron geometry of tetrahedral, but my molecular geometry is bent. So just be aware of this. If you have a molecule that has more than one central atom, I have to isolate each central atom to determine the shape around each one. Now, to give you a 3-dimensional look at this particular molecule, this is what this guy looks like, right? So you can see the carbon atom right here, and then my oxygen atom right here. All right.